Today we start a unit on chemical bonding. There are two types of chemical bonding that occur, and one sort of a subtype. They're ionic bonding, which is what we're going to talk about first, and covalent bonding, which works a little bit differently. And then there's metallic bonding, which is really a sort of a special case of covalent bonding. To understand ionic bonding, we have to understand what ions are. And so today's video is going to be an introduction to the idea of an ion. Ions are small particles that have a charge. Now, by small, we mean atom-sized. They're atom-sized particles. They might be actual atoms that have just been modified slightly, or they also could be little clusters of atoms that we call a polyatomic ion. Today we're going to talk just about the modified atoms, which are called monatomic ions. Since ions all have charge, and there are two charges, positive and negative, we have two different types of ions. Anions are negatively charged ions. It's possible for atoms to become anions if they gain electrons. They have to become more negative to be an anion, to have negative charge, and so anions are formed when atoms gain electrons. Chlorine atoms, for example, have 17 electrons and 17 protons, so they're balanced. Pluses and minuses equal each other out. If a chlorine were to gain an additional electron, well, then you'd have 18 electrons and 17 protons still, and so the negatives would outweigh the positives, and you'd have a negatively charged ion. We'll take a look at how this works, looking at just the highest shell electrons. Electron transfers into a chlorine atom, and it transforms it into a chloride ion. It has a negative charge now. The other kind of ions are called cations. Cations are positively charged ions. So, cations plus anions minus. How can you keep them straight? Well, cation has a T in it, and a T looks like a plus sign. So that's one way to start remembering that cations are positive, anions are negative. Atoms can become cations by losing electrons. So just like atoms can become anions by gaining electrons, if an atom loses an electron, it becomes positively charged. An example would be sodium. A sodium atom has 11 protons and 11 electrons. So a neutral sodium atom is balanced. If that sodium were to lose one electron, it would now have 10 electrons and 11 protons. And so now the pluses would outweigh the minuses. 11 pluses to 10 minuses. And so you'd have a positively charged sodium ion. That's what that would look like using only the highest shell electrons, the dot notation electrons. Sodium transfers its electron out, and now it becomes a cation, a positively charged sodium ion. The electrons that are gained and lost when this process happens, this ionization thing, they're lost only from the shell that's farthest from the nucleus. And that sort of makes common sense, because if an electron is going to leave or enter, where would it leave or enter from? The place that's farthest out, that's closest to the outside world, where the electron is going to go to or come from. Well, these turn out to be the electrons that are shown in the dot notation. So for chlorine, we had the 7 dots, and it was appropriate to show only those 7 dots because nothing happens with the rest of the electrons. That electron is going to get transferred into that spot where there's room for another electron. And with the sodium, which had just a single dot, that electron got transferred out from that highest shell. So it's the electrons that are shown in the dot notation that are involved in the chemistry. There's a name for these electrons. These electrons are called valence electrons. I believe we've used that term before, but we'll use it a lot more now. Valence electrons are the ones that are involved in all the chemistry. They're the ones that are in the highest shell. They're, in other words, the farthest from the nucleus. It turns out that atoms are most stable when they have the electron configuration of a noble gas. And if you think about noble gases, let's just pick one, like neon. Neon has 8 dots. Nearly all the noble gases are surrounded by 8 dots in dot notation. So if you think about chlorine, which had 7 dots, stable for chlorine meant getting another dot, and that's exactly what it did, and it made it negative. Or if you think about sodium, sodium has 1 dot. If I were to take away that highest shell dot, well, then the new highest shell would be, instead of the third one, where this dot is, it would be the second one. So it would be like neon. Here's another way of thinking about this. This is a chart that you may have seen before of ionization energy of elements. And so as we go across, this is the atomic number across the bottom here. It's getting bigger as we go. We see a definite pattern here. Every time there's this increase, a large increase in ionization energy, that's the energy that it takes to take an electron away from an atom, we have a noble gas. So here's element 1, that would be hydrogen. Element 2 is helium. And then it's 3, 4, 5, 6, 7, 8, 9, 10. Element 10 is neon, noble gas. 11, 12, 13, 14, 15, 16, 17, 18, which is argon. And so this pattern continues as we go through the periodic table. Every time we see one of these spikes, we have a noble gas. Well, here's why that's important. Ionization energy is high for things that are stable. The reason that noble gases don't react is because it's hard to take electrons away and it's hard to put electrons in. They're stable the way they are. It takes a lot of energy to take an electron away from a noble gas. So that's why elements become stable when they have the same structure as a noble gas. No room for extra electrons to go in, and it's hard to take extra electrons out. Let's look at a few examples. Here's sodium down here at the bottom. It's one atomic number more than neon. What's stable for sodium? Well, the most stable thing around sodium is neon. So sodium is going to lose that one electron and jump up and have neon's electron structure. By losing an electron, however, it becomes a 1+. Here's chlorine that we looked at. Chlorine is close to argon. The closest noble gas, the closest stable electron configuration it could get is argon. And so chlorine is going to gain an electron to become a 1- ion and have the structure of argon. Here's another one, magnesium. Magnesium is 2 steps farther on the periodic table than neon. So in order to become stable, it's going to go backwards twice. Well, that's going to give it a 2+ charge because it's going to lose 2 electrons. And here's sulfur. Sulfur is 2 steps in front of argon. So 2 steps to argon means losing 2 electrons, and sulfur becomes a 2- ion. And that's a pattern that we could explore in a lot of cases. Now let's take a look at what happens to the dot notation when this process takes place. As sodium becomes an ion, it loses its 1 dot. Chlorine. As chlorine becomes an ion, it fills up the 8 spots for dots. Magnesium. As magnesium became an ion, it lost its 2 dots. Sulfur. Sulfur gained 2 electrons, so it goes from 6 to 8 dots. Now what we see here is that in all cases, you end up with either no dots or 8 dots. And if we did many more examples, we'd find that that's always the case. So atoms that gain electrons to become stable are going to end up with 8 valence electrons. Now there are exceptions, and that's because not all noble gases have 8 dots. Helium has only 2 dots, and so the things that surround helium, that helium is the closest noble gas for, they're going to act a slightly different way. But we won't see that until we investigate covalent bonding. And atoms that lose electrons to become stable are going to lose electrons until they're all out of electrons in their highest shell. And so the lower shell now becomes the valence shell. Like sodium, for example. Sodium had 1 dot. With the loss of that 1 dot, which was a 3s electron, sodium's highest electron is now a 2 electron. So it drops down to the lower shell, and it's 2s2, 2p6. It has the electron structure of neon, which is stable. So no dots is stable, and 8 dots is stable. There's a pattern on the periodic table that makes it really easy to figure out what are going to be the charges of what are called main group elements. So the main group elements are the first 2 groups, group 1 and 2, and then the last 8 groups. And we're going to skip over the transition metals because they behave slightly differently, and they're harder to predict. If you look at the number of dots in each of these columns, well, everything in the column has the same number of dots in its dot notation. Column 1 always has 1 dot. Column 2 always 2 dots, and so on. Remember, no dots is stable, and 8 dots is stable. So you ask yourself, how can I move the fewest electrons around and become stable? And that's what that atom is going to do. So if you look at column number 1, they have 1 dot. it'd be easier for it to lose its 1 dot than to find 7 dots. So it's going to lose 1 electron. That's exactly what's going to happen. When it loses 1 electron, it becomes a +1. So everything in the first column is going to ionize to make a +1 ion. Group 2, it has 2 dots. It could gain 6 or lose 2. Losing 2 is easier to do. So it's going to lose 2 electrons, and that means it will become a 2+ ion. So everything in column number 2 is going to end up being a 2+ ion when it ionizes. Group 3 has 3 dots. That means lose 3 or gain 5. Losing 3 is easier to do. So it's going to lose its 3 electrons, and that ends up being a +3 ion. So aluminum, for example, and boron are going to make 3+ ions when they ionize. Group 4s, that's kind of tough because it's either gain 4 or lose 4. We're going to skip over them. Let's go to the other side of the table. Group 8s are already stable. Let's look at group 7s, the halogens, fluorine, chlorine, bromine, iodine. They have 7 dots. It's lose 7 or gain 1. Gaining 1 electron is the easy way to become stable. It'll have 8 dots. So when it does that, it's gained 1 negative charge, so now it becomes an anion. It's 1-. Moving to the left, group 6. Group 6 has 6 dots. Lose 6 is harder than gain 2. So it will gain 2 electrons, and in doing so become a 2- ion. Group 5. Group 5s have 5 dots. Easier to gain 3 and get 8 than lose 5 and have none, so it'll gain 3 electrons. It gains 3 electrons, it becomes a 3- charge. So nitrogen and phosphorus and everything in group 5, when it ionizes, is going to become a 3- ion. Now group 8s don't ionize at all because they're already stable. They already have 8 dots, or in the case of helium, 2. Group 4s could go either way. Gaining 4 dots is just as easy as losing 4 dots. So we don't really know what's going to happen there. And typically group 4s don't ionize. They will once in a while, but they usually have another way to become stable. And carbon and silicon are fairly famous for doing the other kind of bonding, which is called covalent bonding. So you can probably see a pattern here, remembering that the boundary between metals and nonmetals is right here. We see that on this side of the table, the nonmetals typically are making anions, and on the other side of the boundary, we see a lot of pluses. And so a general rule is metals become cations when they ionize, and nonmetals become anions when they ionize.